Hi, this is part 2 of Wednesday, August 19th's lecture. In this part 2, we're going to introduce a derived unit, and that's volume, and we're going to spend time discussing significant figures and calculations involving significant figures. We addressed our base units in our first lecture on material that we're covering, and we said one base unit that we use is length. Length is a base unit. The base unit that we use in the SI system is the meter. Now, a derived unit is a unit that's derived from one of our base units. Volume is an example of a derived unit. We can derive volume from our base unit, a base unit of length. Now, let's consider a cube. A cube is a geometric shape that has all sides the exact same length. What if we had a cube, and this cube had a length on each side of 1 centimeter? The volume is defined as the side times side times side, or the length of each side cubed. If we take 1 times 1 times 1, we would see that that's 1, and it's discussed as 1 cubic centimeter. It's written 1.0 cm raised to the power of 3. Now that 3 tells us that those units and the values of those units have all been raised to the power of 3. Another way we present that, you might see in a medical setting, is a cc. 1 cubic centimeter is also 1 cc. Now in the laboratory, another unit of volume that we may use and be familiar with a lot is a liter. And this is used extensively in the metric system. A liter is used a lot in lab, and it has a specific definition to it. A liter is equal to the volume occupied by 1,000 grams of water at precisely 4 degrees Celsius. Now, we're going to learn a little bit about conversion factors in section E7. One conversion factor that we're going to use a little bit later is a conversion factor between metric units and English units. In the English system, we typically have quarts, and a liter is pretty close to a quart. 1 quart has 0.946 liters, so a liter is a little smaller than a quart. Let's think about our metric prefixes, because we oftentimes don't use liters in many of our applications. One liter has how many milliliters in it? How many milliliters in a liter? If you look at my PowerPoint, you probably see it. You want to stop it and think about it. There are 1,000 milliliters in 1 liter. Another definition that we also have is that 1 cubic centimeter is equivalent to 1 milliliter. So if you're in a hospital and a nurse says we need 5 cc's of a drug to administer to a patient, what that means is that you need 5 milliliters of a drug to administer to a patient. So that's a derived unit, and that's the end of section E2. Spent a lot of time. We're going to move right into section E3. Copy this. Stop it stop the video at any time that you want. Section E3. Main topic here. It's going to be on significant figures. That's our big topic here, significant figures. Sometimes we might write that as sig-figs. We're going to learn how we can identify significant figures when we look at a piece of data, and also our rules for the mathematics involving significant figures. So significant figures, we need to understand, what are they? Well, when we report data, we're limited to the number of digits that we can report. And that's because we have only a certain level of precision in the measuring device that we're using to make our measurement. That's essentially what it is. Let's write down a good definition of what significant figures are. Significant figures, a really good working definition. These are the numbers of meaningful digits So when I say meaningful digits, these are the number of digits that we know. We know precisely those digits are significant. And we're going to go through an example. So these are all numbers that we know with certainty. Known digits of certainty. And it includes one digit of estimation. So this is the reason why when we report data, we're limited to the number of digits that we can report. We're going to list all the known digits, everything that we know with certainty. And then when we read a measuring device, whether it be a balance in the laboratory or even a ruler, there is one digit of uncertainty, a little level of how we estimate where our values are located. I have an exercise on the PowerPoint. I'm going to go through it. And this would be really important if we were working in a forensics lab. So I worked at a school where we did some forensics. A forensic chemistry class. And we're going to look at the length of a bullet. I'm not a really good artist. So if you look at my PowerPoint, there's a better image. And what we're going to do is we're just going to look at the tip of a bullet. And we're going to look at a scale marking 0, 1, 2, 3, 4, 5, 6. I'm going to end there. And these are in centimeters. And let's put our bullet on this scale marking. Here's our bullet. The edge of it sits there. It comes out. It has this appearance where it tapers down, like right there. That's my bullet. Not the best drawing, but I'm not really an artist. Okay, here's our measuring device. It's a ruler in centimeters. And if you want to stop the video, go right ahead. Go right ahead. But what I want you to do before, when you stop this, think about what is the length of the bullet using this measuring device. Again, the one on the PowerPoint might be a little different, but let's just look at this one I have right here. Stop the video if you want. And okay, if you stopped it, let's think about the length of the bullet. And again, the one on the PowerPoint might be just a little bit different. So this is a little bit different. So we're gonna report the length of the bullet using this measuring device. And again, we're following our rules and understanding why we report a certain number of significant figures. Let's write down all the digits that we know with certainty. We know that the bullet is longer than 5 centimeters. So it's at least 5. And we know that it's less than 6. So we're certain that it's at least 5 centimeters. So this is going to be our length, and we're reporting it in centimeters. Again, it's going to be different on the PowerPoint, so don't freak out if you're like, that's not what it looks like. I'm not a very good artist. So if you want to look at the one on the PowerPoint, it's going to have a different length to it because my drawing skills are lacking. Okay, now we're going to estimate. Let's look at this. Now, when we look at this scale and we're going to estimate between 5 and 6, we normally look somewhere in the middle. Like if it sat directly in the middle, we'd be like it's 5.5. If it's a little bit beyond, we might say 5.6. If it's a little less, we're going to say 5.4. I would say that if I estimate, I would say that that's a little over 5.5, and it's probably closer to 5.6. Now, someone else might look at it and say 5.7, and then you're going to get people that maybe have written down 5.5. That's the level of estimation, the uncertainty in the digits that we're presenting our data with. And that's why we're limited to a certain number of significant figures. Using this scale, you couldn't say 5.624, you couldn't say 5.57, because we can't estimate to the hundredths position. We can only estimate to the tenths position using this scale and the level of precision that it provides for us. Are we good? Okay, let's use a different ruler. Let's use one now that has scale markings. Okay, that gives you an idea of what we're going to do. We're going to put 10 scale markings between each of these. 5.1, 5.2, 5.3, 5.4, 5.5, 5.6, 5.7, 5.8, 5.9. Okay, so I look at my scale marking, and 5.1, 5.2, 5.3, 5.4. There's 5.5. I put a heavy mark on it. 5.6 is there. So someone that said 5.7 might be a little closer. Someone might say 5.69 centimeters. Someone might see it as 5.70. Someone else might see it as 5.71 centimeters. When we have better precision based upon scale markings, we can estimate a greater number of digits. And we can estimate this, in this case, to the hundredths position. So when we look at this bullet now and we have our scale markings, again, the exercise on the PowerPoint is going to be a little bit different. We can estimate to the hundredths position. One person might say 5.69. Another person is going to say 5.7. And notice, since we can estimate to the hundredths, it would be appropriate to write 5.70. And still someone else might see 5.71. So that is the reason why we're limited to a certain number of significant figures when we report data. It's based upon the level of precision that we're making our measurement from, the instruments that we have available to us. We have some rules for identifying significant figures in the data that we're working with. So let's identify some significant figures. And I'm going to just use sig-figs. Identifying sig-figs. So we're going to go through some exercises on identifying the number of significant figures in our data. When the data that we're working with has no zeros, all of the digits are significant. This one has 4 significant figures, 4 sig-figs. Cool. Zeros become a little difficult. They require some rules. Rules for zeros. Zeros are difficult. If we have a number and there's a 0 between non-zero digits, that 0 is significant. 4061, 40.61, 4.061. All of those have 4 significant figures. This 0 is significant when it's between non-zero digits. So far, good. Zeros to the left of the first non-zero digit, not significant. Let's look at a number. Now, these zeros out here are not significant. They simply mark decimal position. This number only has 3 significant figures. We could write this in scientific notation. We move the decimal 1, 2 positions to the right. And when we write this in scientific notation, the portion of the number that we're thinking about is this portion right here. We are not worried about the power of 10. This portion of the number tells us how many significant figures this value has. This value has 3 significant figures. 10 to the negative second is not counted for when we're doing our significant figures. It's only the number that sits to the left of our multiple of 10. We good with that? This number has 3 significant figures. Trailing zeros. Trailing zeros. Zeros that fall at the end of a number after a decimal on the right side, these are significant. This number, 1, 2, 3, 4, 5, has 5 sig-figs. Numbers that don't have decimals. Now, students, we don't like these. They're called ambiguous. We're not 100% sure. 510. This is an ambiguous case. Now, if I gave you a question on an exam and I said, how many significant figures? One correct answer is it's ambiguous. We're not 100% sure. But what do we do know with certainty? For this case, it's ambiguous, but there is some certainty. We do know that those 2 are significant. This number has at least 2 significant figures. Since there is no decimal, we're not sure. So it's an ambiguous case. Now, if you were working through your lab and you found out that this number was given to you in a procedure, and one way to represent this is writing it in scientific notation. 5.1 times 10 to the second. This represents the number of significant figures that we know with certainty. Let's have an exercise. Let's try a few. $3.45. Identify the number of significant figures in each of these. Stop the video, try them on your own, take a second or two. Okay, stop it. Okay, if you stopped it, we're going to go through it. Let's go through our rules. There's a decimal. We have trailing zeros. Those are significant. All the zeros, not just one, all of them to the right are significant. We got 1, 2, 3, 4, 5. 5 sig-figs. Okay. These zeros simply mark decimal position. This is significant. This is significant. A 0 to the right is significant. This is the ambiguous case. We're not sure. So this is ambiguous. Or what we do know, there's at least 2 significant figures. We could write this in scientific notation. So those are our rules for using significant figures. Our next video, we'll go through the mathematics and we'll introduce density. Thanks a lot.